Welcome to the video lecture on FACTS. FACTS is an acronym for Flexible Alternating Current Transmission Systems. It is basically about power control in transmission lines using power electronic devices and circuits. IEEE defines FACTS as alternating current transmission systems incorporating power electronic based and other static controllers to enhance controllability and increase power transfer capability. The need for FACTS controllers arises due to various reasons. Day by day, the power system interconnections are getting complex, and the existing control devices called circuit breakers are not fast enough to control power flow during emergency situations. Secondly, in order to meet the increasing power demands, constructing new lines is become difficult because of right of way and cost constraints. So, the power transfer capacity of the existing lines has to be enhanced. Using FACTS controllers, we can enable a line to carry power closer to its thermal ratings. Normally, in the absence of such high speed FACTS controllers, a transmission line carries power very less than its rated value because there is always a margin put to meet a sudden inrise of currents due to faulty conditions. Such faulty currents can be easily controlled in the presence of FACTS controller, so we need not place any margin. Also, every power system has a self regulation. Generation always should balance the load. If generation is less than the load, the voltage and frequency drop, and thereby the load goes down to equal generation again. This is called self regulation. However, there is only a few percent margin for such self regulation. Consequently, the voltage or frequency may collapse. FACTS can avoid such issues by virtue of its high speed control. Before we proceed towards understanding various FACTS controllers, it is imperative to know the structure of the existing power systems. Case 1 shows parallel paths. Here, figure A shows a system which is an uncontrolled system basically. There are two buses connected by two parallel lines, and the power flow from surplus generation area to the other side depends entirely on the line impedances. A upper line has impedance X and the lower line has impedance 2X. According to current division rule, the upper line will carry 2/3 of total power and the lower line will carry 1/3 of the total power. The second case, figure B, shows a line with a HVDC transmission. So, in such a case, the electronic control of power is possible because of rectifier and inverter circuits. So, we can have better control and we can make the line, HVDC line, carry power closer to its thermal capacity. Figure C and D also show the cases of two systems with FACTS controllers. Figure C shows a series capacitor in second line, and figure D shows a phase angle regulator in the second line. So, wherever these regulators are placed, power flow control is possible. Case 2 of a power system is a meshed system. A basic network is shown here having three buses and three transmission lines. A, B, C are the buses. A, B, BC and AC are the transmission lines having impedances of 10 ohms, 5 ohms and 10 ohms respectively. Also, the maximum ratings of these lines are AB 1000 megawatts, BC 1250 megawatts and AC is 2000 megawatts. But based on the line impedances, they are carrying powers of 600 megawatts, 1400 megawatts and 1600 megawatts. By using superposition theorem, we can get these values. Here I have shown the superposition principle implementation here. Case 1 is where the generation at A is retained, but generation at B is removed, the source at B is removed, and powers are calculated. We get a P1, that means line AC power as 1200, P2 and P3 as 800 megawatts. In case 2, we remove the generation at A and put the generation at B back. In this case, we get the powers P1, P2 according to current division rule as 200 megawatts and P3 will be 800 megawatts. Finally, based upon superposition principle, we combine these two cases. The total power in the transmission line AC will be 1400 megawatts. The in line AB it is 600, and in line BC it is 1600 megawatts. We have seen that the rating of the line BC is 1250 only, so it is carrying 1600 megawatts here. That means it is overloaded. But the lines AB and AC are normally loaded. They are less than, they are carrying power less than their ratings. In order to rectify this problem, to remove the overload, we have two solutions. One is to reduce the generation at B and increase the generation at A. That involves the generation operators. Instead of that, the second method is by implementing some changes in the transmission line itself. We can do this. That means 2000 megawatts at A and 1000 megawatts generation at B are retained, and we try to modify the transmission line parameters to modify the powers flowing through them. This is the slide which shows these changes. The line BC, the line AC is having in the figure B a capacitor of 5 ohms inserted. So already it is having an internal impedance of 10 ohms. When you connect a capacitor in series, its impedance will decrease to 5 ohms. So that will result in all these powers changing. AC will carry now 1750, AB 200, 250, and BC 1250 megawatts. So you can see that the power at in transmission line BC is reduced from 1600 to 1250 megawatts. So the same powers can be achieved in another way, but that is by making a changes in line BC by putting a reactor in series with the transmission line BC of 7 ohms impedance. So consequently, the impedance of the transmission line BC will change to 12 ohms, and here again you will get 1250 megawatts flowing in through the transmission line BC. The same values can be obtained by inserting a phase angle regulator in line AC. So in this manner, power flow control is possible by implementing some changes by placing a reactor or a capacitor or a phase angle regulator. In addition to what is not shown in this slide, we can achieve power flow control by injecting a voltage in a transmission line. These are the loading capability limits of a transmission line: thermal limits, dielectric limits, and stability limits. Stability limits are classified into many types based upon the time frame: transient stability, dynamic stability, steady state stability, frequency collapse, voltage collapse, and subsynchronous resonance. These are a few parameters which we will try to improve by incorporating FACTS controller in the power system. This figure shows the power flow and dynamic stability considerations of a line. A simple line is chosen having two buses, and both the buses carry generators as well as load. The bus 1 voltage is even at a power angle of delta 1, and bus 2 voltage is E2 delta 2. So the real and reactive power flows in the transmission line can be calculated easily based upon the basic laws. Figure B shows a phasor diagram relating E1 and E2 voltages. So the difference of these two voltages is the drop in transmission line EL, and the current flow through the transmission line I is nothing but a vector perpendicular to the line EL always. Figure C shows the various the phasor diagram showing the various relationship between the active and reactive currents. Here we are assuming that delta 2 is 0 and delta 1 is delta. So a vector E2 is drawn in parallel along the x-axis, and E1 is drawn with an angle delta with respect to the x-axis. Then the components of E1 and E2 are E1 sin delta and E1 cos delta. Similarly, the components of E2 are E2 cos delta and E2 sin delta. You know that the cos delta component is in phase with the vector itself, and the sin delta component is perpendicular. So altogether we find that the resultant of these vectors e2 cos delta and e1 is e1 minus e2 cos delta, and e2 minus e1 cos delta is shown along x-axis. The currents, corresponding currents is also shown. Finally, we get the real current of transmission line 2 as IP2 equal to E1 sin delta by X. Similarly, the real component of I1 IP1 is E2 sin delta by X. Multiplying this with the respective voltages, we get P1 as E1 E2 sin delta by X, and P2 also E1 E2 sin delta by X. Similarly, we will get the reactive powers also from the equations vectors E1 minus E2 cos delta and E2 minus E1 cos delta. Figure D shows the power versus angle relationship. It is a half sine curve. 90 degrees is the point where instant where angle where we get maximum power. So P equal to E1 E2 by X sin delta. P max is E1 E2 by X. By varying X, the reactance in the line, we can change the P max value, the level of the curve. And the figure E here, vector diagram E here shows the injection of increase in the voltage, bus voltage E1, which is resulting in changing of the vector E1 minus E2, orientation of the vector. Consequently, the current vector I also changes its orientation. So it shows that when you change a bus voltage, whether it is E1 or E2, you cause a change in reactive power flow, not much change in active power. You also see the phasor diagram F here, where a voltage is injected in series with the line here, E1 minus E2. When you inject a voltage in series with the line, then the length of the vector E1 minus E2 is as if increasing, so your current is increasing in length, not the angle. So that means there is active power control here, not reactive power control. Finally, we have the phasor diagram in figure G, which is showing injected voltage having in any other relationship. It can be in phase with E1, it can be in phase with E1 minus E2, or it can occupy any angle. The circle injects the locus of the various injected voltage vectors. So this involves change in the both length of the current vector and also the orientation of current vector. That means there is a change in the reactive and reactive powers as well. So all that is described in the vector forms is listed out here, the various controllable parameters. Control of line impedance, X controls, provides the current control. Control of angle provides a means of controlling the active power flow. Injecting a voltage in series with the line provides active power control. Injecting a voltage in series with the line and with any phase angle provides both active and reactive power control. And injecting a voltage at a bus, near a bus E1 or E2 will involve only reactive power change. These are the diagrams of various types of fax controllers. Figure A indicates the basic diagram of illustration of a representation of a fax controller. A thyristor within a box indicates the symbol of fax controller. Figure B is a series controller which is injecting a voltage E in series with the transmission line, and figure C shows a shunt controller injecting a current at the point of connection in the transmission line. Figure D is a combination of two series controllers. Then figure E is a combination of series and shunt controller controlled in a coordinated manner. Figure F shows the combination of series and shunt control with a common DC power link. It is called UPFC. Similarly, GHIJ shows various other types of fax controllers. Benefits from fax controllers, obviously we have seen that control of power flow as ordered, increase in the loading capability of lines, increase in the system security because transient stability limits etc. are increased, and providing secure tie line connections to neighboring utilities, providing greater flexibility in siting new generations, upgrade of lines, reduction of reduced reactive power flows, reduction of loop flows, and increasing the utilization of least cost generation because basically we are strengthening the transmission interconnections by using fax controllers. Finally, the requirements and characteristics of power devices. There are three requirements: voltage and current ratings, losses, and then finally parameter trade offs. The voltage and current ratings of a typical 125 millimeter device are 3000 to 4000 amperes, and voltage ratings of 6000 to 10,000 volts. Normally, voltage source converters are used in the advanced day fax controllers, in which the devices used are asymmetric turn off devices which have turn off capability but no reverse voltage capability. This feature is preferred because if there is no reverse voltage capability requirement, the device can be made thinner. Otherwise, it will be bulkier. And so, in order to obtain the reverse voltage withstand capability in an asymmetric device, you can connect a diode in anti-parallel. Losses are of three types: conduction losses, switching losses, and gate driver power losses. Conduction losses are due to forward voltage drop. They have to be rapidly removed from the wafer through the package and cooling medium. This involves high cost. Similarly, switching losses during turn on, the forward current rises before the forward voltage falls, and during turn off of the devices, the forward voltage falls before the current falls. So there is a simultaneous existence of high voltage and high current in the devices. This represents switching power losses. And the gate driver power and energy requirement are very important part of the losses, and total equipment cost also. Switching speed, the transition from on state to off state with high dV by dt and from off state to on state with high di by dt. These are very important parameters. They dictate the size, cost, and losses of a snubber circuit. So this snubber circuit also is a part of important part of the total equipment cost. Finally, we have to make a trade-off, a compromise between various device ratings, the voltage and current capability, gate power requirements, di by dt and dv by dt capabilities, turn on and turn off times, turn on and turn off capabilities, uniformity of characteristics for parallel operation, quality of silicon wafers, the class of clean environment. So all these against the cost have to be selected carefully. So that is the end of part 1 of fax controllers. Thank you.